Hello everyone, this is Jen Zahid, and today I'll be explaining the Slinky drop lab report. So to introduce, the purpose of this lab is to analyze the motion of a falling Slinky, and specifically the motion of the bottom of the Slinky as it falls down, and just observe how it stays stationary. So I used a digital Slinky model through VS Code, and I used Tracker to track a video that was provided to us, and through that I was able to illustrate the concepts of resistive force, gravitational force, and drag. And this lab will focus heavily on Newton's second law of motion, and also a preview of the result is that the bottom of the Slinky stays stationary due to the unique net force that it experiences. Here are a few equations that I use. There's the F net equation, the F net of all the other possible force combinations, and the force of drag. So these are the initial conditions. This was the initial velocity of the Slinky, the initial position, the stretched Slinky length, and the mass. So the system included only the Slinky and the surroundings. I wanted it to be to include the Earth, the air resistance, and all other external forces that are acting on the Slinky. And for the main physics ideas, again, I explored the Newton's second law of motion, and because it represents how momentum or the motion of the Slinky is affected due to the net force that is acting on the object, and it shows how that time takes into play over time. And also, I have used these equations to interpret the effect of Newton's second law. So I use F net equals Ft plus F drag, and then F net equals dp/dt, which is just change in momentum of the F, which is update of velocity, F of drag, and F of tension, because tension was like the gravitational force that it was experiencing, and how weight is the Fg that's acting on the Slinky. That's the force from the Earth. So here's explanation of code. So for the first bit of code, that was a setup and the constants. So this section, I divided the Slinky into 15 segments, and I was just setting the mass per segment, the stretch length, the k of the spring, the dt, and the time, the initial time, and just setting up constants like g. And then for the second part, I initialized the Slinky segments. So I made the segments, or I represented the segments of the Slinky as small spheres in order to show how every segment is moving. And each segment has an initial velocity and acceleration of 0. And I represented that through the code. And then here I defined the air resistance force. This is just k dot the magnitude of velocity times velocity, which is just velocity squared. And then this is a simulation loop. This took the most time. So in this loop, I made sure that for every time step, I first took in mind the gravity that it pulls each segment down, and that there's air resistance that slows each segment, and also there's spring force that pulls each segment towards its neighbors. And I updated the acceleration, velocity, and position of each segment, and you can see the velocity and, acceleration and displacement update formulas in here. Here's running the code. So from the VS Code, as you can see, I just ran it, and then these are the segments that are moving, and then you can see the graphs that are modeled now. So this is the position time graph, the velocity time graph. You can see the acceleration going into because of drag force, it's going to terminal velocity, and the acceleration, of course, going to 0. Here's tracking the motion of the Slinky. So I used the video that was provided and the tracker software, and you can see the timestamps on the Slinky as I edited them, and then you can see the graphs on the right of the data that I plotted and used. So that was all. And then here are the tracker graphs for the displacement, acceleration, and velocity of the data I obtained. And then you can see how y is changing, and then the velocity is reaching like a terminal velocity. Of course, it's not perfect, but you can see that. And acceleration too, it's approaching 0. We can see during the last few segments. And here are the GlowScript graphs from the model that I've created. So these are the same graphs you saw before in the video, but these are just screenshots. And you can see that the acceleration goes to 0, the position goes down because it's like in the negative direction, and you can see the velocity reaching terminal velocity as the F net goes to 0. So in terms of similarities and differences between the real life model and the model that's like computational, is that there's a segmented structure. So each part of the Slinky moves on its own. For gravity and air resistance, both models face gravity and air resistance as resistive forces, and also there are distinct base movements because of the end of the Slinky and how it stays stationary throughout the whole movement. For the differences, the spring force approximation. So we assume that the spring force is uniform between segments in the code because that was simpler for us to implement. But in real life, it really varies depending on the time that you look at the spring and or the Slinky and how it moves. And also for the air resistance calculation, so I used a linear drag model because that was easier to like use, and I used the constant air resistance coefficient. But in real life, air resistance is just more dynamic and it changes throughout the motion, just like the spring force. And also there was a simplified 1D motion that the code took because it assumed that the each segment just moves vertically. But in real life, it wobbles and it twists and it just moves all over the place, which we saw in the real life model. Possible errors include oversimplifying air resistance. And this could cause inaccuracies in timing and speed of the segments that they fall. And this is shown in the code and also the real life example, because in real life example, if we were tracking all these stuff, it would have been very more complicated. And also where there might be some accuracy errors because we assumed uniform spring constant for like the uniform spring constant might be off by a little bit. And also we neglected the rotational lateral movements, so that can account for some of the errors we saw in the graphs. They were not major errors, but they can interfere with the data just a little bit. So for my what if question, I asked, what if we apply this model to explore the dynamics of other chain-like objects like varying gravitational fields on like other planets or microgravity? So if we apply this model to other gravitational environments, that would reveal how the distribution of forces in flexible chain-like objects under different gravitational strengths, just like a spring. And for example, a planet with stronger gravity with hovering effects might diminish more quickly as a gravitational acceleration would put all segments down faster. But in microgravity, for example, the model would show more pronounced oscillations and slow convergence of segments, like the 50 segments we talked about earlier. And gravity would barely pull all the segments down. So it really depends on the environments you're talking about. Also, for what does it mean? Basically, I asked the question, what does it mean for the model to treat each segment as an independent point mass with individual forces instead of modeling the Slinky as a continuum or like a whole object? Is that treating the Slinky as an individual point mass assumes that each coil behaves independently, which simplifies calculations, but also it sacrifices a lot of the accuracy. But I see that, or in my opinion, I see that looking at the Slinky as like different segments that move independently is very important, as we can understand the motion of the Slinky more profoundly and exhibits more complex like wave propagation, and it better reflects how forces in the real life or real world distribute in flexible and interconnected structure. And this is all about the trade-off of using either a simpler model or a more complex model that exhibits real life function. That's all for today. Thank you for watching.